Welcome to this lecture series in general topology. In this lecture, we'll learn the notion of a subbasis, which is a weaker version of the notion of a basis. And we'll get to that. All we need to know is what is meant by the topology generated by a set. We have talked about it multiple times, so no point reiterating. And we need to know what is meant by basis for a topology and the connection between, or not the connection, but how you talk about continuity when there is a basis that generates the topology that one is dealing with. Okay, so let's proceed. Here are some problems for practice. This is a very important problem. It shows you that the notion of continuity could have been framed equivalently by using closed sets rather than open sets. Okay, but a very simple problem. And so let's move on. So subbasis. Fix a set X, then a collection of subsets of X is called a subbasis on X if, underwhelmingly, the union of all the things in script S is all of the set. So very, very weak definition. All you're saying that it is a cover. If you've seen the notion of cover in real analysis, then you would agree that all this is saying that a subbasis is a cover of X. That's all. Whatever, so this is the formal definition. Unclear why this is even useful for us. But let me remark that, trivially, every basis is a subbasis. Because already in the definition of a basis, this clause that all the elements of a basis together, their union is everything, is already present. So a basis is clearly a subbasis. Okay. Now for the somewhat interesting lemma, you pick any subbasis. So this is script S on a set X, and define script B as this object. What is it? You pick a finite subset out of the given collection, which is a subbasis, and intersect all of them. And you do this for every finite subcollection. So script B is nothing but those sets which can be formed by intersecting finitely many elements of script S. That's what script B is. All right. So then, interestingly, which I wouldn't even guess on the fly, or if I were first introduced to this definition, I wouldn't guess that B turns out to be a basis, even though the reduction is pretty easy. Basis on X, and further, very importantly, the topology generated by also the topology generated, it's not going to be horizontal, generated by script S is same as the topology generated by script B. Okay. So this is what we want to show. It's a very, very simple fact. You should take this as an exercise before you look at what I'm going to do. So first, why is this guy a basis? Why is this a basis? Well, we should note that this is obvious, that script S is contained in script B. What is script B? It is those sets which can be written as intersection of finitely many things in S. Now, if you pick only one element from S, that is also a finite subcollection. And if you intersect one element, then you're just having that same element, that same member of S. So every member of script S is there in script B. So this is there. And so to show that this is a basis, all we now need to do is that if we pick two elements from here which intersect in some set, and we pick a point in the intersection, then we need to show that there is some other element here which is contained in the intersection and contains the point. So I'm just recalling the definition of a basis. Okay, so to show that B is a basis, let B1 and B2 be chosen in script B such that their intersection is non-empty, and let X be an element in their intersection chosen arbitrarily. We want to show that, or need to show that, there is some element in script B such that, right, maybe again I'll draw a picture. So this is B1, that is B2, and we have chosen a point X. And we want to show that there is some B which contains X and is contained in the intersection. Now say B1 is equal to intersection, and similarly B2 is this intersection where these are finite subsets of our subbasis, right? Every element of script B can be written in this fashion. That's the definition of script B. So we have that. And now just declare or define B as this intersection. So B is just this entire thing. This entire intersection is B. And clearly B is also is there in script B, because what is B? B is this intersection. And this is a finite set. It's the union of two finite sets. So this is a finite set which is contained in script S. So we are intersecting only finitely many things from script S, and therefore B is also an element of script B. And that's it. That finishes the job. So this shows that this is a basis. And now for the second part, why is the topology generated by this is same as the topology generated by that? Well, first of all, the topology generated by this is contained in the topology generated by that. That's because the set itself is, the subbasis itself is contained in the basis. So if a collection of subsets is contained in some other collection, then the topology generated by this collection is contained in the topology generated by that collection, clearly. So that's that. Why is it that everything in the topology generated by this is also in the topology generated by that? Why is that? Well, the topology generated by this guy certainly contains script B. So here is the statement. So for the second part, let tau be the topology generated by script S, and theta be the topology generated by script B. Note that tau contains script B, because any topology is closed under taking finite intersections. Tau contains S in particular, so it contains all those sets which can be formed by taking finite intersections of elements of S, and those are precisely the sets that are there in script B by definition of script B. So this containment is there, but this is a topology, and if a topology contains a bunch of sets, it will also contain the topology generated by that set. So this implies tau contains the topology generated by, right? Because this is the intersection of all the topologies that contain it. Tau is one particular topology that contains it. So this containment is obvious. And we already argued that this containment is there. So this was already argued. This containment was there. And this is by definition theta. So we have a sandwich. Theta is contained in tau is contained in theta. So this sandwich shows that tau is equal to theta. And that's it. So that proves this blue fact. All right, very simple lemma, but a useful one. This notion of a subbasis, as you can see, it is another gadget to develop the topology or define the topology or construct a topology on a set. Just come up with a subbasis. Then you can take the topology generated by it. Of course, it's just a collection of sets after all. But we also have somewhat of a good handle on that topology because we have an explicit description of a basis which generates the same topology. And that's very useful. And we'll see an example to justify the usefulness of it. Okay. Now let's see a criterion or a fact which relates continuity with subbases. So this time we have topological spaces x and y and a function or a map between x and y. And let this be a subbasis for the topology on y. Now what does that mean? It just means that is the topology generated by script s. Well, script s is a subbasis and the topology generated by it is the topology that y came with, is the topology on y. So y was a topological space, it has its own topology. S is a subbasis such that the topology generated by the subbasis is same as the topology on y. So this is a collection of some subsets of y whose union is all of y, such that the topology generated by this collection is same as the topology that y has. All right, then the following two facts are equivalent, or following two statements are equivalent, not facts, but statements. First is that f is a continuous function. And second is that f takes pre-images of the subbasis elements to open sets in the domain. So just like we had a criterion for bases, we have a similar criterion for subbases, and it's equally convenient. In fact, it's even more convenient because a subbasis can be significantly poorer than a basis. It's much easier to check these for a smaller collection of sets. Fine, so the power of this will be apparent as we go along, but for now, let's try to prove this somewhat abstract statement. So first of all, this is clear because if f is continuous, then it takes, or pre-images of open sets here are open in X. That's the global criterion for continuity. We have seen that. And every element of script S is open in Y because the topology on Y is same as the topology generated by S. So every element in script S is open in Y, and therefore 2 holds. So this is the clear, this is very, very obvious. Now for the other direction, for this direction, let script B be the basis determined by S, by which I mean, as in the previous lemma, script B is the collection of all those sets which appear as finite intersections, or which appear as intersections of finitely many elements in script S. So by this somewhat vague or imprecise statement, I mean that the B as it was defined in the previous lemma, previous slide. Okay, so this be the basis determined by S, and pick some arbitrary basis element. Now since we know that, and by the previous lemma we know that the topology generated by this guy is same as the topology generated by that guy, so now we pass the buck to bases. We know that to show continuity of the function f, all we need to do is show that every element of this guy, or the pre-image of any element of this guy, is open in X. Because the topology generated by this is same as the topology that is there on Y, because it is same as the topology generated by S. So all we need to do is just show that the pre-image of this arbitrary element chosen in the basis is open in X. So enough to prove that, enough to show that this is open. in X, which, let me remind you, is just another way of saying that this is in the topology on X. Okay. Now, by definition of script B, B is this set for some, for some finite set, script F contained in script S. Okay. And thus, what is F inverse B? F inverse B is F inverse of this intersection. But elementary set theory gives you that this last thing is this. Oops. This is equal to that. Now this is open in X by hypothesis. So this is open in X for each S, since if S is in script F, S is also in script S. So this is open in X. And we are intersecting only finitely many such things because this is a finite set. And therefore this is open in X. And that's it. We've shown that this is open in X, and that is what we wanted to do. So the proof was trivial, but still I wanted to give full details. Okay, lastly, let us look at an example. So, for two real numbers a and b, with a less than b as depicted in this figure, define va comma b as all the points x comma y in R2 with x in this range. So if you visualize, this is a vertical strip like such. It is all the points which are depicted in this red thing. So maybe I should even draw something like that, or at least try to draw. I don't know how I'm going to manage. And now for the shading part. So this shaded part depicts what we just talked about. Right, clearly. I mean, not much to say there, although my lines don't seem to be parallel. It doesn't seem vertical, which will bother me for the rest of my day. But let me now try to fix it. Okay, what is going on here? All right. Yeah. Now, similarly, we define the horizontal strips. For two real numbers c and d with c less than d, define the horizontal, I mean hc comma d, h for horizontal, v for vertical. H of c comma d is defined as all those points in R2 with y lying in this range. And again, I want to draw a diagram. Right, so hopefully this figure conveys the idea. All right, and here is the thing. If you define script S as the collection of all the vertical strips and all the horizontal strips together, then this is a subbasis. Subbasis simply because it covers everything clearly, but it generates the same topology as the standard topology on the plane on R2. Because if you just intersect two of the things, meaning one vertical strip and one horizontal strip, what you will get is a box-like object, rectangular box, and each of those boxes is clearly an open set in R2 in the standard topology, right? Because every element in script S is open. This is an open set in the standard topology in R2, and this is also an open set in the standard topology on R2. Take that as an exercise if that is not immediately clear. And therefore, every element here is already open in R2, and every square, every open square, or rather every ball in R2 under the infinity distance is there in S. So let me write that statement. For each x in R2 and r greater than 0, we have that the infinity ball with center x and radius r is there in script S. Not in script S, but in the topology generated by script S. In topology generated by script S. Right? So suppose x is my point somewhere. So, okay, maybe I'll explain in another diagram. Let me just explain it. No point writing a formal proof of what I just wrote. So suppose x is somewhere here. And we have this infinity ball. Recall, this is how infinity balls look like with center x. So you just take this horizontal strip and you take that vertical strip and intersect. And that is clearly there in the topology generated by S. And therefore this guy there is this little square, this infinity ball, open infinity ball, this infinity ball is there in the topology generated by S. So the topology generated by S contains every infinity ball, and hence it contains the topology generated by the infinity balls. The topology generated by S contains all infinity balls, and hence contains the topology generated by all the infinity balls. So let me just be sloppy and write it that way. Right? If it contains a collection of sets, it also contains the topology generated by that collection, simply because the topology generated by any collection of sets is the intersection of all the topologies that contain it. This is one particular topology that contains that. So the topology generated by this collection is necessarily contained here. This argument we gave on the previous page also, or maybe on the first lemma. So this is there, but this is the standard topology. So at the very least, the topology generated by S contains the standard topology. But why is it that this is contained in the standard topology? Well, as we said, every element of script S is already open in the standard topology. So the topology generated by S cannot be strictly finer than the standard topology. The standard topology already contains script S, and the topology generated by script S is the intersection of all the topologies that contain script S. Standard topology is already one such topology, so this containment, that this is contained in the standard topology, is also clear. So we have shown perfectly rigorously that the topology generated by this particular subbasis is same as the standard topology on R2. So we can say this is a subbasis for the topology on R2, because when we say topology on R2 without any qualification, we mean the standard topology on R2. So wonderful, we have another way of looking at the topology on R2, and you can extend this construction or this consideration to higher dimensional Euclidean spaces. This is for R2, but you can talk about or do the same thing for Rn, and I encourage you to do it. Try to write it down formally. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.